Hi, everybody. My name is Matthias Rettenmeier, and I brought along Tobias. We're both with Zalando, placed here in Hamburg, and we're going to talk about understanding customer journeys with deep learning. And what I mean by this, this is going to be the talk. Same title, different slide. So we're actually, we're part of Zalando, and but we're based here in Hamburg. Tobias and I are both data scientists. And before I get into this, we've structured the talk a little bit that I'll give you a short intro on what Zalando is and what we're doing here in Hamburg, and then lead you towards one of our problems we're working on currently. And then I'll hand it over to Tobias, who will go into more detail. So, who are we as a company? I think most of you perceive us as an e-commerce site or a fashion company. We certainly are a fashion company, but not entirely. So, we were founded in 2008. Currently, we have more than 10,000 employees. And this is where it gets interesting. We have 7 tech hubs throughout Europe already, and over 1,300 tech employees. So we're sort of also a tech company. And we operate in 15 countries. We have 22 or about 22 million app downloads and over 19 million customers. So we're a fairly big e-commerce site, and we're not only a fashion company, but also a tech company. As just mentioned, we have several tech hubs throughout Europe, and we extended towards Dublin and Helsinki last year, and also have a tech hub in Hamburg now. And how we got to Hamburg, I will give you a little bit more insights. We have also another tech hub in Dortmund and a lot of other locations throughout Berlin, and a lot of operational and logistic stuff throughout Germany. But for tech, it's basically Berlin, Helsinki, Dublin, Dortmund, and now also Hamburg. And here in Hamburg, we do Adtech, so technology for advertisement or online advertisement. And we call ourselves Adtech Lab Hamburg. We started off here in Hamburg, not as Zalando, but as Metrigo, and we're doing real-time advertising. So we created the technology to partake in real-time bidding, and we were then acquired in March 2015 by Zalando. We're fairly small compared to the large amount of employees based in Berlin, so we're only about 20 guys, data scientists, engineers, and also some product managers, but mostly engineers. And we're growing, so plans are to add another 20 employees later this year. So I've mentioned online advertising, and maybe to clarify this a little bit, what I mean by this is actually display advertising. So you all know banners, and they can either be off-site or can be on the site itself. So we build technology that is concerned with delivering ads to the right people at the right time. So our question is, who do we show ads and when? And what is our target audience? And beforehand, when we were still Metrigo, we did this in the real-time bidding context. And we now, as part of Zalando, moved into a slightly different direction. And one of the products that came out of it, I want to talk about a little bit today. And we showcase the problems we're having there, or the challenges we're facing. So this one product is ZMS Custom Audiences. And ZMS stands for Zalando Media Solutions. It is basically the idea to provide ad tech solutions for our partner brands and future clients. So we built ad technology with a very strong focus on fashion and built products around that which we then offer to our partner brands. And how this could look like, so we have our e-commerce site, and we do have categories. We have a lot of products on the site. And so, for example, we have casual stuff, party, apparel, trendy fashion items, and young fashion. And just to show a use case, we are trying to estimate something about how likely are you to purchase a female party dress within the next few days. So if you're male, there's probably no propensity to do so at all. If you're female, there might be a chance. And we're trying to figure this out to create a specific target audience towards this topic. So mainly, the question is, where's the party? And where are you in the journey? So in general, this is a problem coming from advertising. We want to create a specific target audience for our brand. And now I'm going to get into a little bit more detail on how we proceed and how we do this and come up with an example problem formulation, which Tobias will get into later on. So as I said before, we have a fairly large e-commerce site with 90 million customers. And what we do is we log a lot of the clickstream data. So actions on the site are logged. And for this, we've built an event-based infrastructure. And so you visit the Zalando site, you interact with the site, and actions are recorded and sent to our tracking endpoints. And from there, they're passed on to a Kafka queue. And this Kafka queue is basically organized around various topics depending on where the event data comes from. So it's not only the e-commerce site, but it's also our customer-facing applications for mobile. And we have several of them, and everything feeds into one event queue. We then take these events and we consume them from within AWS and store them there to AWS's simple storage solution. We've done quite some experience with this. Zalando's general approach, as we've become a company that is embracing radical agility, and we have a lot of small teams that basically act autonomous. We've also decided to switch over to AWS to allow teams to have their own infrastructure, and we not depend on any centralized infrastructure at Zalando. So this is why we put our data into AWS. And when we created this workflow, we first started with simple JSON, moved to Afro as a file format, and then came up with Parquet because for us, or for our use case, it seemed to be the most efficient in terms of storage, and also with its column-based storage approach, one where we don't have to access all the data at the same time, but we can select different columns that are of interest to us. So basically, we've built entire infrastructure around tracking events. And what this looks like is that we get over time, we just get various different events from various different users across Europe, and then in the order of the time. So whenever somebody looks at a product, adds a product to the basket, looks at the catalog, clicks something on my feed, which is sort of like a recommended product feed on Zalando, this stuff will be recorded by our backend systems. And why do we need this data? Well, this is what we use to actually learn from the users that interact with our sites and our customer-facing applications. And then we try to make sense out of this data to create target audiences for our brand customers, to show relevant ads to the people who are basically interested. Yeah, so what we have is all this event data, and this is in the scale of terabytes. And we somehow have to work with that data and or efficiently work with the data. And so we have created a data aggregation workflow for the machine learning tasks we have. And what it essentially does is it takes the event-based data and encodes them as customer journeys, or that what we call customer journeys. It is basically the data pivoted by user. And by user, I mean cookie ID. So we use cookies for tracking, and the data is just aggregated by users so that we can see how the journey for a customer is over time. Since we stored the data in AWS, we also use AWS tools to do so. And we adopted the EMR approach to spin up Spark clusters, crunch the data, pivoted by user ID, and then extract the relevant information. And then we store this in something we call a feature matrix. And feature matrices, I don't know how many are accustomed to data science topics, but this is essentially the input we feed into our models, our machine learning models. So again, we take all this data, we group it by user, and then we take out the relevant information, we create features, and store that in a compact format. And we do this all with Spark on EMR clusters in AWS. And what we get out is, instead of terabytes of data, just gigabytes of data. And why this is important is, okay, step back. Again, so the pivoting actually delivers something like this. So we get, instead of having all these events from all different users, we get something like a timeline for a specific cookie. So, for example, someone looked at his My Feed in the morning, clicked like, did some action on the shop, went to work, maybe saw an ad impression, went back home, maybe saw another one, then went back to the site and did some more interactions and looked at products and stuff like that. So this is what we call a customer journey, and this is what comes out of our aggregation jobs with the information on top that we need for our processing. So now we have the data stripped down to the user level. We have stripped out the irrelevant information, and we ended up with something we call the feature matrix, and only consists of a couple, maybe tenth of gigabytes. We then, for our research, move away from AWS. We've experimented with the AWS ML frameworks, but decided to go offline. And we have, or out of the cloud, we have in Berlin a HPC cluster with very high performance graphic cards. And for the application at hand, where Tobias is going to talk a little bit more about, compute power is very important, and it's a very compute-intense task, and we can leverage the performance of GPUs there. So we reduce the data to the feature matrix and the essence. We take it out of the cloud, put it on our HPC cluster, and then we do model training, optimization, see how we can adapt the models in order to make a prediction of how likely a person is to do, for example, or to come back to the beginning example, to buy a party dress. And this information we use to create target audiences that we then can offer to our customers or to our clients for marketing purposes. We've come quite a way on creating this workflow, and the reason to split between event aggregation and machine learning or model training on a HPC computer was mainly due to the special requirements of each task. So when we're in the cloud and when we aggregate the data, we just need a large set of machines to crunch through Parquet files and pull out the essence. In the machine learning context, we just need a lot of raw power to actually train the models and generate the output that we want to have. So model training, we decided to go with Torch. It's an open source package, machine learning package. It was is I think heavily in use with at Facebook, and it was also used with DeepMind before TensorFlow came along. So yeah, this is what we use as tool chain to get from raw data to a finished model. And overall, the process then looks like we get the data from the site, we feed it into our Kafka event stream, we log it to, or we consume it to AWS S3. Then we aggregate the data by cookie, or pivot the data by cookie, so we get cookie histories. Then we transform the data to feature matrices, and then we take it out of the cloud and do our model training and prediction to create something like a target audience. And we do this on the HPC cluster, or on specialized machine on AWS, but usually on the HPC cluster. So I want to talk about, briefly, before Tobias gets into more detail, about one example use case. I talked about the party dress. It was a little bit high level. So one goal for an advertiser could be to target customers who are likely to purchase within some category. And we formulate this as the probability of someone to order who just came into the store. So if you go to Zalando, we want to find out how likely is it that you purchase something within your visit. And this we try to model with our machine learning models, and Tobias is going to talk about it now, how this is done in practice.
Okay, can you hear me? Yep, you can. All right, so by the way, I hope you all are Zalando customers, and maybe someone of you recognize himself here. So the idea is we want to predict these order probabilities, okay? So we want to say, how likely are you, how likely is it that you're going to order something? Which information do we have about you? So basically, we don't have information about you, but about the cookie. And so we have the information about your history. So what have you done before and during the last time steps or so? For instance, you had some ads, you clicked on some ads, you had some product views, so there's plenty of products on the Zalando page, and you looked at one. You had another product view, and you put something in your cart. And then the question is, for instance, given all this information we have about this cookie, how likely are you going to order something within the next 7 days? Yeah. So and how can we predict stuff? We can predict stuff with a great, fancy, hype machine learning, of course. Yeah. But the question is, how can we get such a cookie history into a machine learning model? So such a history by itself, it contains a lot of information. And most importantly, it's sequential information. Now the big question is, how can we get such a thing into a machine learning model? So what's done traditionally? Traditionally, what is done is there's an engine of handcrafted features. So for instance, so we could build a feature which says, okay, we could look at our data and think, okay, what's important maybe for a model to predict orders? So for instance, whether there was already an order during the last 7 days. Makes sense. But if there was an order, maybe then it's not so likely that you will have another order. Alternatively, you could, for instance, look at did you look at really many product detail pages? So if you looked at a lot of products, then it's probably quite likely that you're going to order something, and so on. Do you have many orders and many items in your cart already? So then it's also likely that you order something. So basically, this is all features which we as a human being craft, okay? So this is what usually is done in traditional machine learning. We think about our domain and try to represent it in a really clever way by means of features. Okay, and so what is basically a feature in the end is basically what we see here on the right is basically just a feature vector. So it's basically just a vector of numbers. And then we can put this vector of numbers into a machine learning model. For instance, into a logistic regression, random forest, SVM, you name it. So there's this zoo of models. For instance, if you check the sklearn website, you can always try out 20 different ones. And more or less, they are all vector-based. So vector-based means the input is such a vector of numbers, and then in some clever way, they try to detect some patterns in these numbers and make a prediction from this. So that's the traditional machine learning approach. So, and here comes, this big hype word, deep learning. So deep learning has been all around. You probably have heard about it, and maybe you're already a bit tired of it. But in the end, it really makes a lot of sense, and there's really a lot we can gain from deep learning. So just as a first warm-up, so what does deep learning mean? So learning is always machine learning. So the machine learns some patterns and can predict something. And deep means, in this case, we have many different computational layers. So many different computational steps, one after the other, until we calculate in the end the final prediction. So this is why it's called deep learning. And deep learning is basically just a really, really wide word, and it comes in two different flavors. There's convolution neural nets and recurrent neural nets. One could also imagine other ones, but these are the two prominent paradigms. So when you hear about what's convolutional neural nets, they are used mainly in vision. There's, of course, also different applications, for instance, also in language or so. But basically what it does is mostly standard application is looking at an image and trying to understand, for instance, what object is in the image. So what you see here on the left is basically a cascade of different layers, which look at always more bigger neighborhoods. So that's one part of convolution of deep learning. That's the part we're not interested in here. We are interested here in the second part. That's why we'll talk longer about the second part. So it's recurrent neural networks. So the really great thing about recurrent neural networks is that they are a natural way to feed sequential data into a machine learning model. So we, as data scientists, paid by Zalando also, we don't have to come up with features ourselves, but we basically just throw the raw data, more or less raw, into the machine learning model, and then the machine learning model learns something. Okay, but so overall, recurrent neural networks are really practical for all sorts of sequential data. So they are, for instance, they are on your telephone, so on your Android or your iPhone is working, so the speech recognition is based on recurrent neural networks. Yeah, and so basically, what is a recurrent neural networks? It's a sequence of cells, so to say, computational units in a sequence, and they get at every timestamp, they get an input. Here it's the X, and then they can also produce at each timestamp an output, or at the very end, they could also only produce at the very end an output. So that's the idea overall in neural networks. So, about recurrent neural networks. Okay, so I will spare you here the mathematical details, but that's the overall abstract idea. So how can we make use of it for cookie histories? So basically, we have here this cookie history, and we can basically just insert or input the individual events, so for instance, the ad click or the product view, into the net itself. So basically, what we would say, for instance, we would tell the net, okay, we would encode the ad click as maybe as event 17, type 17, or our product view as type 15 or so, and then input into the RNN, into the recurrent neural network. And then the recurrent neural network itself, it computes latent states or cell states. So there's different names for this. So this computational unit, it has a state. It's basically, again, it's just a vector. By the way, it is usually a quite low-dimensional vector. In our case, we will show experiments later. It's only 10-dimensional. It's really small. But the great thing is, so it models, so to say, what do we know about the user, or the cookie, in this case the cookie, until this very particular point in time. So in the end, what we have is here in the end, in orange, we have a final vector which encapsulates or compresses all the information that we have so far seen. Basically, it encapsulates all the information we have from this cookie history. Okay? And why is this such a great thing? There's no feature engineering here. So we just give it to the net, and the net does it by itself. So again, I spare you the details. So basically the net is, or cell is basically it's like a big equation. So there's plenty of matrix multiplications and some nonlinear functions involved. And these matrix multiplications, they contain a lot of parameters. And in learning, these parameters are set to specific values such that our specific problem is solved in the best possible way, or in a good way, if learning was successful. Yeah? So that's that's overall always the idea in machine learning. So what the point is, there's no magic, or no special magic at least, involved in here. It's basically just a mathematical equation, which is then for which the parameters are optimized. And in our case, what we optimize is we want to predict, or we want to maximize basically we have our prediction problem is that we want to predict like sales, orders. And this is for we train our model such that it can do it, the RNNs can do it in the best possible way. Okay, so again, just to recapitulate, so there's two different types of approaches. So there's the traditional one, I call it the traditional one, is here is the engine of handcrafted features. And the alternative is these deep learning methods. And so this is really, maybe it appears to me for you to a small step, but for machine learners or for machine actually it's a really big step. Since we get rid of all this by hand feature engineering. So as a side remark, so for instance, Pedro Domingos, that's one of the most famous MLers, machine learners, he wrote a book about machine learners, but he says, for instance, 80% of value that a machine learner can deliver is by feature engineering. So it makes also sense as we know the world quite well. So when we can bring a lot of our knowledge into the model, that's really good. But with deep learning, we can there's a way to model to learn better from the raw data themselves. So that's really a big step from a machine learning point of view, and also for humankind as well, of course. Yeah. And to show to convince you even more of deep learning, we have performed some experiments. So Zalando has plenty of European countries, of course, and we chose 2 of them, and we looked at data from spring this year, and we looked at plenty of sessions. And then basically what we try to do, we want to predict, given a session start, how likely is it that you're going to order something. So we had a couple of weeks for the training phase, and then later on some couples of weeks for testing. Okay, and here's just some results. So it's really, there's not a lot of time to go into detail here, but basically it shows, just give you a glimpse of our results. So there's machine learners love a lot of figures. So I'm a machine learner, so I also love a lot of figures, and it's always the same. So what the guy talks about is always better than the other thing. Yeah, so this is also the case here. So I'm talking about the red stuff, so about the RNN. So so what do we see here? We have done experiments in 2 countries, and basically what it tells, we are comparing 2 methods, the one with the handcrafted features and the RNN. So these 2 approaches I showed you beforehand. Okay? And so the metric here is AUC, area under curve. I will not go into detail about it here. It's just a standard machine learning metric to say whether the model is good or bad. So here it means the higher the better. So what we see here overall is that RNNs are as good or better than the handcrafted features. Maybe a really important thing to say is here, so this light orange, these handcrafted features, it's not just really bad features, but this is our, so to say, our old production model. So this is the old model we use, where we spend hours and hours and months for feature engineering. Feature engineering usually is a constant process. You work on it constantly. New data comes in, you think about different kinds of features, you do experiments, A/B tests, and so on, do data, experiments on historical data. So here in this case, it's really quite sophisticated handcrafted features, but still the RNN can be as good as, yeah. So and also I show on the right side for country 2, I just show different types of models. So you have the neural net basically, so the second column is a non-linear model, but using also vector-based handcrafted features. And there's, you can make also these RNNs more complicated by stacking individual layers, but this is not important here. So the base message is, by means of RNNs, we can be at least as good as by doing all these months of feature engineering by hand. Okay? So machines can do it as the same stuff what we can do with our brains. Yeah. Okay, I've already told you a lot about these 2 different types. Here's a wrap-up. Okay, so on the left we have logistic regression, on the right we have recurrent neural networks. So I haven't talked a lot about logistic regression, so basically it's the standard method for using, or standard machine learning method, but it's just here an example for a vector-based machine learning method. Okay, so that's the traditional one on the left side with the handcrafted features. On the right side we have the recurrent neural networks. So left, handcrafted features, right, learned. So the accuracy for the left one comes in by our human domain knowledge. So for instance, we know So for instance, I'm very much into fashion and e-commerce, so I can craft very good handcrafted features, but the accuracy of the model only comes by means of my knowledge. In contrast, on the right side, everything is, so the accuracy of the model is really due to full machine learning. Then on the one, okay, of course, then model tuning is much easier for the vector-based approaches because we have already done most of the job by means of our handcrafted feature engineering. In contrast, recurrent neural networks requires more sophisticated model tuning, so you need to look more. It's more difficult, and it's, so you have to set more parameters and make more experiments. And of course, also training is slower. But this is quite clear because it has to learn everything by itself. In contrast, logistic regression also, or handcrafted features, training is fast because basically we did all the job already. And again, so fast prediction is quite fast, in this case for logistic regression. And for RNNs, I will not go into details here, but it depends also on the representation. What you do can be really slow or can be faster. And now maybe, so this talk is also about, has the great title, Understanding Customer Journeys Using Deep Learning. So now this is what I turn to now. So this is the last point. The interpretation, so what one often says in logistic regression is, oh, wonderful. So just for maybe you know about it, so I have these different parameters for the individual features. Perfect, I can just say which feature is important, which one is not. Actually, this is most often wrong, because you cannot interpret these features directly, or the weights, or the coefficients directly, if features are correlated. So this is getting a bit technical, but in the end, what I want to say is, it's not like logistic regression or vector-based methods are really totally easy to understand in contrast to deep learning. This is not the case. Still, in deep learning methods, there's really these big neural networks with plenty of weights and parameters. They are really hard to interpret by themselves, so these parameters. But the really wonderful thing is you can visualize things quite well. And this is what we turn to now. Yeah. So basically, this is what an RNN looks like when it's doing its job, and in practice when it works. Yeah. So what do we see here? Okay, so the label of the x-axis got missing. So what we see on the x-axis is goes from left to right. It's a history of a cookie. Okay, cookie so cookie basically always means a user in the end. So user does certain actions on the Zalando website. Yeah, for instance, in the beginning, the user looks a lot at different catalog pages. For instance, looks, I don't know, for black Zalando t-shirts or whatever, and then he finds someone or she finds something and goes on a PDP, product detail page, again to the catalog, and so on and so forth. And we feed each of these steps can be fed into the RNN directly. And then this is basically what's happening on the x-axis. Again, also I put also with the distance and the timings, so it happens after 2 minutes, after 1 minute, and so on. Okay, now there's 10 different gray lines. Maybe while I've been talking during the last minute, you've already thought to make sense of these lines. It's really difficult to make sense of these lines. Basically, it's more or less not possible. Yeah? It's really, I mean, these are basically this cell state, if you remember some slides ago, the cell state of the recurrent neural network. So this is the vector that represents all the information that the network has so far about this customer. Okay? And what we see here, in orange, there's a lot going on in these cell states. So the recurrent neural network is really excited, something is really going on, and the values change, and so up and down, and so something really great is happening. And what great stuff is happening? So for instance, here, the great stuff on the left side is somebody's putting something into the cart, or looks at the cart, or puts something on the wish list. And these are exactly the events we love at Zalando. If you put stuff on the wish list, because then you're really likely to buy stuff, and then we get paid our salary or so. Yeah? So that's what we really like, and that's why this RNN is also quite excited. So more seriously, so this network has learned to detect the important events by itself. Okay, so the events that are important to predict order probability. And here on the right side, you can all see there's a checkout and a sale. So basically, then it also changes. There's a lot also going on, because if there's a sale, of course, this also has a lot of influence on your order prediction probability. So, and the great thing is, you can, if you see this, now you can translate this directly without additional cost. You can translate it directly into probabilities. So that's the really wonderful thing about RNNs, or deep learning in this case. So we can directly feed the individual events into into the RNN, and we directly get at each timestamp without additional cost, we get the order probabilities out. So for instance, what we see here with the orange boxes, here a lot of is going on in the orange boxes, and this is also where these order probabilities show significant changes. So for instance, here on the left box, you see, okay, there's a lot of going on. There's something going into the cart or into the wish list, and then the order probability increases a lot. In contrast, on the right, the person made a sale, bought something, had an order already, so the probability drops immediately because it's not so likely that you're going to order very soon thereafter because you just ordered, okay? And all this has learned the model by itself just from the raw events. Just as a side remark, in principle, of course, you could do the very same thing also with logistic regression, SVMs, and so on, but the problem is you would need to recalculate all the features at each single time step. And here, it comes for free. So that's the big difference. So and this gives you a means. So in e-commerce, it's always the big thing. Oh, what's the customer journey? How do people behave? Do they first look at this, and then they buy something? So that's really the big miracle or big myth. Or the interesting thing, of course, because this is how we make our money. But yeah, this gives you a quantitative means to better understand these customer journeys. Okay, and I also show you more slides with an alternative representation. I haven't told you about a lot of details about this, but what we look at here is sessions. So on the x-axis, what you see are individual sessions. So here I've shown 15 sessions of a customer. So the oldest session is on the very left, and the last session is on the very right, with session -1. So it was 0.1 days ago. How much there was? 2 hours or something. And yeah. And you have the different sessions, so there's an alternative representation so these events are already grouped into sessions, but then the whole session is just given to the RNN. And the idea behind it is that often in e-commerce one is also interested in this idea of thinking of session journeys. Oh, so there's the session where you come to Zalando and you want to get inspired, then there's the next session where you want to make price comparisons, and then there's the third session where you're going to buy something, yeah, without voucher, I hope, yeah. So there's in this case we have two different. I'll show you two different. I emphasize two different sessions again in orange, and these are again sessions which are really interesting for the neural net because there's a lot going on in the cell state. So what are these sessions? For instance, the first one on the left is just a session where a sale happened. And the right one is a Zalando dream because there's a customer for 2.5 hours at Zalando and basically does more or less all Zalando events that you can imagine. Yeah, so it's really great. And this also you can directly translate into order probabilities. So basically into what our model predicts. So on the left side, here for instance we see again a drop because there was a sale and it goes down. And on the right side, plenty of events happening, so it goes up from 30% to 50% to that the customer or the underlying cookie is going to buy something. Yeah. So that's the cool thing with RNNs. So to wrap up, so overall, what Matthias has presented to you is that we have this modular data processing pipeline, and this makes all our research very flexible. So that's a really important thing in data science, and especially when you're doing machine learning, you want to have a really fast turnaround time. Because actually, it's a lot of trial error on machine learning, where you need to try out new data sources, and there's so many different ways you can do experiments and you can prepare your data. So what you want in the end is you want to be really fast and flexible in what you do. And what Matthias has presented to you is that this enables us to do a lot of experiments. And then what I've told you about are these deep learning. So deep learning hype word, but in the end, it makes a lot of sense. It's a great thing. Recurrent neural networks are a generic tool to model customer behavior directly from the raw event stream. So we don't have to do all this feature engineering, but it comes out directly. And also these RNNs allow, what I've shown you in these visualizations, they also allow to better understand important events, and that's the important thing, in a quantitative way. So it's not like of course we have this intuition, okay, if a user is a long time at Zalando, of course the likelihood will increase. But this gives us really precise numbers. Gives us exactness and accuracy. That's a really great thing. So accuracy is really important everywhere, but especially in all this advertisement and real-time bidding context, because this is what you base your bids on. So basically what you pay. Yeah. Okay, maybe as a side remark, so if you of course, it's more with RNNs, it's more complicated. I don't want to say that logistic regression feature engineering doesn't make sense. Makes perfect sense, especially given the current state nowadays in 2016. All this deep learning is only about to start. So if you want to get things fast, or if you do it for the first time, it makes perfect sense to do feature engineering. But I think the future is RNNs, because then machines can learn more by themselves. And we cannot compete with these machines because just the machine can try out so many different things. We can only, basically, they can just think much faster because they can try out so many different possibilities. It's no wonder that they can be better. Yeah, that was it about our talk. Of course, we have the obligatory hiring slide. So come to our booth. We have a booth behind there, so you can talk to us. We have office in Hamburg. We are hiring back-end, front-end, data science, and so on. Yeah, and yeah, come and talk to us. Is there another slide? Yeah, and that's the final slide. All right, thank you very much. So everything's clear? Oh no. Please wait for the microphone. I remember.
Okay, thank you very much for the talk. It was very interesting. So just to get this right, one thing is the only thing you're pushing to the neural network is the user saw a product, an A category, and put something into the basket, but you're not pushing particular products. So it doesn't give you any insights on the product that was, but just the probability if he's gonna buy anything, right?
Yeah, for this particular use case, yes. We do have, different advertising products, and we're still expanding those, and some are very specifically targeted to a specific product in the shop, and they would also contain product information.
Okay, maybe to say something to this. So with the product, this is basically, we don't use it yet in both things, because for our use case it's not relevant, but again, we could use it, but in both ways. We could engineer features which says, for instance, I don't know how many products of brands Adidas or so did the user look at and so on, so we could do feature engineering, or we could put the, let's say, the identity of the product or the category also directly into the RNN. But we haven't researched it yet. It still requires, yeah, this will be our future research, actually. Yeah.
Second question is, does the RNN also take into account the time between the events?
Yes, okay, yes, it's totally necessary. So I've, yeah, so let's look, for instance, here. I've written it here. So what we put into the RNN here is a difference to the previous timestamp. Yeah. So actually, there's some slight feature processing, pre-processing if you want. So for instance, we don't give absolute timestamps, but we give already the difference. So it's not totally raw, but it's kind of raw. Yeah. But the time difference is very different, of course.
So there was this huge drop after the sale, where the prediction for another sale would be really low. I could tell this right away to you without machine learning, I suppose. But do you put in data you, as a human being, know yourself that works, and as a second channel to the machine, or are you just predicting it by the machine?
Okay, you're saying a very interesting thing. This is, you know that it works. So maybe first of all, when one sets up an RNN project or machine learning project, one first does toy experiments with artificial data, or often it makes sense to do this, where one controls the data and knows what's going to come out. So this just the beginning for the machine learning research. Besides now, for such a model, we cannot put data into it for which we know the result because we don't know it. Yeah? Of course, we have a strong intuition. That's why I put it here in orange, and that's why I put it to the slide, because I think we all share the intuition. Okay, there was a sale, so there will not be another one. But in general, we just don't know in quantitative exact terms. We don't have a model how human beings work. For Zalando, in general also not, but also not for Zalando, yeah. So in the end, we cannot put some data for which we exactly know, oh, this must be probability 57 and this must be probability 12. We can't do this.
Marketing is like, I don't know, 70 years, 90 years old. Are you just reinventing what has already been invented, maybe?
No, not at all. So what is... Okay. I must say this, okay, how do I say it in the most neutral way? Okay, marketing is often not a very accurate, exact discipline. Actually, there's a lot of funny things going on in marketing overall, not at Zalando specifically, but overall, which are when you're coming from natural science. Yeah. So this, okay, to make it more clearer, for instance here, these quantitative ways to really say, okay, this probability 57 or 50 or 40, this is really important. For instance, in real-time bidding, real-time bidding is the thing where you can directly bid on advertisements. You can say, for instance, when you go to FAZ.de and we want to show you an ad for Zalando, we can say, okay, for you, we would pay €1 or 50 cents or so. And we base this on the probability. So if our probability estimate is only better by, I don't know, 3 or 4%, this saves us a lot of money. And this cannot be done with human intuition. This is where machines win.
One of the things that I was wondering about, you're doing all this amazing work with like deep learning and etc. Why are you using cookies? I mean, come on. You have people who are purchasing stuff. They have to create accounts to make wish lists, whatever. Why don't you, use maybe like user IDs or etc. to match customer data across devices?
You have not talked to a data privacy person. So. Yeah, it's privacy.
Yeah, and so for advertising, like the relational databases we have on the customer, we don't use for advertising.
Yeah, well, you're not allowed to use these.
Yeah. No, it's different for.
I know your age and where you live. Come on.
Yeah. It's different for stuff around delivering the services on site, yeah. But for advertising and marketing and stuff we sell to the outside, it's a different story. So yeah. There we only use cookies. Essentially for us, cookie tracking is just storing a user ID or a cookie ID. There's not more that is stored in the cookie. It's just one ID.
Okay, there's another question. There's plenty.
Just continuing on this one, do you try to align different cookies so to make some cross-device detection from a handy and the session continues on the desktop PC at home? So this is neutral to privacy issues.
Currently not. No, there's effort to do probabilistic cookie matching stuff, but we currently don't.
That's the time of short answers.
Yeah.
One question to the sessions. How do you determine the session length? So when does a session start and when does it stop?
It's not a clear concept by itself. So there's not a such thing as a session. It's again some sort of small feature engineering here. So in Zalando universe, what we Zalandos often do is that we say there's a new session when there's just a sequence when you're idle for 30 minutes, so when nothing's happening, and then with the next event. But it's totally made up. Yeah. So there's no such thing as an abstract, platonic session or so. So yeah.
It's the idea of a visit to our site, or an interaction with the Zalando site, and we call it session for whatever reason.
Okay, yeah. Thank you very much.
Thanks.
Bye at Zalando.